Everyone to the third session of this short course in randomized matrix computation. And let's welcome Professor Joel Tropp again.
Good morning. Oh, not necessary. All right. So I appreciate your persistence. To recap, we've been talking about different strategies for designing algorithms for linear algebra computations using probability theory. In the first session, we talked about Monte Carlo approximation methods where we construct an unbiased estimator for the quantity of interest, which is easy to get your hands on, and then we average independent copies to reduce the variance. So we saw two applications, first to a scalar problem, which is implicit trace estimation, and second to a matrix problem of approximating the outer product of a matrix with a lot of columns with itself. And we saw that in both of those cases it was easy to construct an estimator, and by averaging we could get interesting approximation guarantees in settings that seem like we couldn't achieve with deterministic methods. In the second session, we talked about random initialization, the idea that if you start an iterative algorithm at a random point, you can hopefully ensure a favorable trajectory for that algorithm. So the first example we discussed was the randomized power method for estimating the maximum eigenvalue of a positive semi-definite matrix. And we saw that the random starting vector had two favorable properties. It is a little bit aligned with the maximum eigenvector, and it is not too aligned with any of the other eigenvectors. And as a consequence of these two phenomena, the algorithm works for a little while before it makes any progress. There's a burn-in period, and then it eventually locks on and starts converging to the maximum eigenvalue. And we saw that that's true regardless of whether or not there's a gap between the largest eigenvalues. So that was a result that seems to have been discovered by researchers who are studying the randomized version of the algorithm. It wasn't part of the classical analysis. Second of all, we studied the randomized SVD for producing a low-rank approximation of a matrix. In this case, we multiply the matrix by a random test matrix and use the information we collect about the range of the matrix to produce an inexpensive approximation. The reason this algorithm works is because the random test matrix tends to be somewhat aligned with the leading right singular vectors of the matrix, and it's not too aligned with the trailing right singular vectors of the matrix. So that random initialization ensures these properties, and we saw that we were able to obtain a competitive approximation bound even with this very simple method. And if you would like this to be an iterative algorithm, you could repeat this process by repeatedly multiplying this random test matrix into the matrix you're approximating and its transpose. And by doing so, you can drive the error down farther. So make it a little bit more like the power method. We didn't talk about that. So in this case, we start with a random point, and the properties of that random initialization are essential for the rest of the algorithm, which is deterministic. There's no more randomness after that. Today we're going to talk about another strategy, progress on average, where we make random choices at each step of an iterative algorithm in the hope of making a small improvement, at least in a typical step. And the principle here is that we will, as I said, design iterative algorithms that make random choices at each step to reduce an error or something like that in expectation. Okay. So the error in both of the examples we're going to talk about today, the error really is an approximation error. So it's really something you can understand as something you would like to chew away at each step. Each time you want to drive the error down little by little until it goes to 0. But there are other settings where you might have a potential function that isn't directly related to what you're trying to achieve, and you're trying to drive the potential down little by little. Okay, so you all know of at least one algorithm that has this flavor, which is
SGD.
Stochastic gradient descent. So stochastic gradient descent, what does this do? To solve the convex unconstrained problem, minimize f of x, we start at an initial point, x naught, which is somewhere, could be random, doesn't have to be. And at each step, we make an update of the form xt plus 1 equals xt minus some step size eta times some vector g of t, where g of t is random, and on average, it equals the gradient of the function f at the current iterate. So instead of taking a regular gradient step, we're instead producing a random vector, which on average equals the gradient, and we'll take a step in that random direction instead of taking a step in the actual gradient direction. And of course, the reason this is valuable is that it might be a lot cheaper to estimate the gradient randomly than to compute the full gradient. That's especially true if f is a sum of a bunch of terms, as happens in most machine learning problems. And what happens with this algorithm? I'm just going to draw a schematic rather than writing down any theorems or anything. So you've got level sets of this convex function, which maybe look like this. You start at some point, x naught, and what does the algorithm do? Gradient descent, of course, would move in a direction that's orthogonal to the contour line, but because we are taking a random step, we hope it's pointed the right direction on average, and so we're moving maybe this way. Maybe we accidentally go this way sometimes, but eventually this trajectory will move toward the optimal set, and then we'll maybe bounce around here in the optimal set. But we've obtained, hopefully in the limit, a solution to this convex optimization problem. And the way this works, theoretically, is that on average, at each step, we reduce the distance to the optimal set. And so this is a very simple example of a procedure that does exactly what I described, which of course is one of the most widely used algorithms in optimization these days. Okay, great. So we want to talk about some applications in linear algebra. And the first example is really going to be stochastic gradient descent in disguise, applied to a very specific linear algebra problem, which is over determined least squares. And I'll explain to you as we discuss this why the algorithm we talk about really is just stochastic gradient descent in disguise, but we'll do an analysis of this method that's adapted to the problem at hand. And then after that, we'll talk about an algorithm for low-rank matrix approximation that is also based on this principle of making steady progress on average toward the solution. Okay, great. Any questions before we continue? Y'all are lively this morning. Okay. So, the first thing that I want to talk about today is the randomized catch-marts algorithm. which is for solving overdetermined least squares problems. So I'll write down the problem and talk a bit more about the setting. So this is a very old algorithm. This dates back to at least 1938. And it was popular for a long time in the literature on tomography, where you have a bunch of measurements that are potentially wildly inconsistent with each other, and somehow you'd like to fit an estimate for an image using those horrible, horrible measurements. This algorithm was also widely used in digital signal processing. I would say that these days it is perhaps more useful as an illustration than an actual numerical method, but it is quite elegant. So I hope you find this interesting. So we're going to let A be an n by d matrix where n, the number of rows, is much bigger than the number of columns. So the picture here is that A looks like this. And we're going to write AI for the transpose for the rows. So I'm explicitly putting the transpose on here. So these are transposes of column vectors. And so these rows are in RD. And we are going to let B in Rn be a response variable. So this is the right-hand side of the least squares problem. And the goal here is to solve the minimization problem, minimize over x in Rd, half the sum from I equals 1 to n, the squared error in each of the equations. So this is, of course, just a fancy way of writing ax minus b, L2 norm squared 1/2. So we're going to try and find x that minimizes this objective. Okay? And I've written it out in some form for a reason that will become clear. Okay, great. So any questions on the setup here? It's a very standard problem. Okay, so this, again, is designed for the setting where there are a ton of rows. And the idea is that we are going to be enforcing equations involving each of the rows one at a time without reference to the others. And so you can imagine if you had a ton of these equations, and they're presented to you one after the next, that you could scramble every time you see a new equation and try and solve that equation and see whether you can eventually approach a solution to the least squares problem. Okay, so here's the catch marks iteration. According to my notes, it's actually 1937. So how does this work? Well, we start out with an initial iterate, x naught in Rd. If you don't know any better, you could just pick 0. And at each step, we select an equation, j of t, t is a time index, and we're going to enforce that equation. So what does that mean? We're going to take the current iterate xt to be the previous iterate minus a correction, which I'll write out and then explain. Here's the correction, and it is in the direction of the selected row of the matrix A. So at each step, we take the previous iterate, we move in a direction which is given by the row that we have chosen, and we have this funny step size here. And we do this for, sorry, the index is t. For t equal 1, 2, 3, and so forth. Okay, so the first thing I want to say about this iteration is that this step size is not arbitrary. It is chosen so that the inner product between the selected row and the new iterate is exactly equal to the response value. Okay? So we have updated the variable x so that the selected equation, j, holds exactly. Okay? So that's what this particular choice of constant achieves for you, those special step size. And this is something that you can work out quickly for yourself. Yeah.
This is not the same as recursive least squares, right?
No, probably not. Okay. More questions? Okay, so the step size here is chosen to exactly solve the equation that you've selected. And you can also see that this is a gradient step in the direction given by the jth equation. Okay, so we're basically just taking a step in the direction of the negative gradient of this equation that we have picked out. And the step size here is chosen so that we have this special property. Okay, so you can see this really is a type of gradient descent scheme where we're only choosing partial coordinate-wise updates. Okay, good. Any questions about what this algorithm does? All right. Now, how long does a step take? Well, this variable has dimension d, and we compute an inner product of some d-dimensional vectors, and we normalize things, and we update the d-dimensional decision variable. So this is just an order d operation here. So this is order d for every iteration. So it's a relatively cheap update. Okay? And so the hope is that we don't have to do too many updates to get a reasonable solution to the problem. And so when you think about n as being extraordinarily large, you're hoping that somehow the cost depends more on the dimension d of the variable rather than the total number n of equations. Okay? So that's the idea here. Good. Now, there's something missing in the specification. What's missing? Yeah?
How to select like JT.
Yeah, the control rule. So tell me, Pavlos, how would you like to select J of t?
I would use randomly.
Okay. That is a good idea. And perhaps you had that idea because we were talking about randomized linear algebra algorithms that make progress on average. And perhaps it's because you know about stochastic gradient. How would you have thought to do this if you were Catchmarts?
One after the other, the entire list.
Sorry, what?
One after the other, the entire list.
That's exactly right. So what did Catchmarts say? Well, he said, I'm going to choose JT to be T mod n. So I'm just going to cycle through the equations in the order given over and over and over and over and over again. Okay, so this is called cyclic control. I don't know why they use a specific language, but it's what they call it. All right, now if you're slightly more clever, you might say, well, why do I care about the order these equations were given to me? And you could permute them. So you could also do a random cycle where jt is equal to pi t mod n, where pi is a random permutation. Okay. This is actually something that people did quite a lot. This is actually quite effective. Works significantly better than this most of the time. Something else you could try and do. Any other ideas? What other control rules come to mind? Yeah, you could. Uniform. This is an interesting strategy, but there are reasons that I'll try and explain that this might not be the best way to go about it. There's another classical rule I'm looking for.
Different random pi.
Different random pi, what?
Pick the one that has like the biggest difference.
Perfect. So a Gauss-Southwell rule, okay? So worst equation. So you pick the equation that has the biggest deficit and you fix the deficit. Okay, that's very expensive. You got to look at all the equations and check all the deficits. But people used to try and do this. Okay, so the problem with most of these, aside from this one, is that these are very hard to analyze. But they all converge. So if you run this algorithm, any of these control rules, you'll get an xt that converges to some kind of solution to this least squares problem, maybe under some extra assumptions. So that's good, but on the other hand, if you want to understand what this algorithm is doing or how the properties of the matrix A intermediate in the performance of the algorithm, it's very hard to figure that out in this setting. So instead, we're going to consider a random control rule, which is was proposed by Stromer and Verschinen in 2008 or something. And what they proposed is that at each step, we're going to pick jt to be a random variable, and it's going to equal rho I with probability proportional to the energy in the ith row. And then we need a normalization factor that accounts for the total energy in the matrix A. Okay. And so what we think about here is we look at how big each of these rows is. We take that as a measure of importance, and we sample each equation with probability that is proportional to its importance. Okay? Importance being measured by the squared L2 norm. So this is a form of importance sampling. And we do this independently in each step. So each row selected is independent of all of the previous rows. That'll make our analysis a lot easier. Okay. Great. Any questions on what the rule does? Yeah.
What's the motivation for that importance metric?
The proof. Yeah.
Okay. Sweet.
Yeah. Yeah, you'll see that this is somehow the right measure of importance. So there's always some amount of creativity in all of this. You're thinking to yourself, well, how do I make this work? When we're talking about Monte Carlo approximation, you're like, well, why do we have this set of importance sampling probabilities when I'm building a matrix approximation? Oh, well, I want to sample the important stuff. What does important mean? Oh, it should cancel something out in this formula. Yeah. Yeah. So there's actually a fair amount of cleverness involved in developing these algorithms, even when the strategies are sort of natural. Okay. Other questions?
So you can normalize each row with a norm of AI and divide BI by the norm. And then if the equation gets same, then that becomes just same as uniform sampling.
Yeah, yeah, that's right. If you rescaled all of the rows so they had equal norm, and you rescaled the response variables to account for that, yes, you could use uniform sampling.
I see.
Absolutely. It's a slightly different problem, though, and the analysis is actually going to lead to a different conclusion, potentially. So just a warning. OK, good. How much does it cost to work out these sampling probabilities? In the worst case, you need to look at every entry of the matrix. And so it might be an order dn operation. This is actually going to be the most expensive part of the algorithm. So you would be a lot happier if you, for example, had rows that all had the same norm, so you didn't have to do this. All right, good. So what I'd like to do now is show you the analysis that Stromer and Vershinen developed. It's a bit simpler than the analysis of stochastic gradient descent because these least squares problems are very simple. Yeah.
Question.
Yeah.
If you like randomly sampled rows of A, well,
Yep.
to like approximate the Frobenius norm, so you would do better than ODN, but you wouldn't. Yeah, I guess you would only have an approximation of the denominator. Could you still analyze that, or?
I'm not really aware of good shortcuts here because this is about as cheap as anything that you can do that looks at the matrix. So this is sort of the fundamental problem. You could say, I'm going to try and sample some entries or something like that and hope that that gives you some picture about what's going on, but that requires a lot of assumptions. So yeah, so one of the weak points here is the computation of sampling probabilities might cost you something. Okay, more questions? Okay, so here is a theorem which is due to Stromer and Vershinen on the performance of this algorithm. So they're going to make some assumptions, which we will also carry with us. So we're going to assume that A is injective. So it has full column rank. This ensures that there aren't potential manifold of solutions, a linear subspace, an affine space of solutions. And we're also going to assume that B belongs to the range of A. So the right-hand side is exactly representable. There are analyses that go beyond these assumptions, but this makes our lives easier. And this ensures that there is a unique solution X star to the equations. So we're moving away from least squares toward an overdetermined system of linear equations. And you have to think harder if you want to deal with the least squares case. But this is still a somewhat interesting problem. Now, we're going to define an error measure that we would like to make progress on. There are different kinds of error measures here. You could imagine that the objective function is the thing we're trying to drive down. And we could eventually get to 0 because these equations are consistent. Instead, we're going to do the same thing that you do when you study stochastic gradient. We're going to define the error to be the distance from the current iterate to the unique optimal point. Okay? So how far away are we from the actual solution? And the claim is that, on average, the error in the algorithm is bounded by, yeah, let's do it this way. 1 minus a number that I will define in a second to the t power times the initial error. Sorry, that's the worst 2 ever. Okay, so you can kind of see what's happening here. We're going to prove this by showing that at every step we reduce the error by this factor. That's progress on average. And you'll see that, of course, after t steps, you obtain t copies of this factor. Okay. Now, what is this factor? So kappa dem is called the Demel condition number of the matrix. And it is defined to be the Frobenius norm squared divided by the minimum singular value. Oh, sorry, no square. Yeah. So this is a relative of the ordinary spectral condition number, where in the top you would have the maximum singular value of the matrix. And the Frobenius norm is at most square root d bigger than that. But it actually could be significantly smaller as well. Okay? So it's somehow a flavor of condition number for a matrix that somehow takes into account the energy in the matrix in a more delicate way than the ordinary condition number for linear systems. Okay, good. So this is a statement of the result that we're going to prove. And let me give you a little bit of intuition about what this means. So the interpretation here is that if the number of iterations t is bigger than twice the square of the Demel condition number times log 1 over epsilon, so we see exponential conversions here, then the expectation of the error is at most epsilon. So the number of steps we need to drive the error in our least squares solution, the distance from the actual optimal point down to epsilon, depends on the conditioning of the matrix, which is not surprising. We know that if you want to solve linear systems and get the solution vector correct, that you have to pay for the stability of the problem, which is measured by a condition number. And we only pay weakly for the error level that we're trying to achieve. We get linear or exponential convergence toward that optimal point. So to understand what's going on here, you can imagine that if the ordinary condition number kappa A is constant, so the matrix is pretty well conditioned, then the Demel condition number, kappa dem, is equal to order root d. And you can see that because, as I said, this is at most square root of the number of columns times the maximum singular value. And what that tells us is that in this special case, to get error epsilon, you need about d log 1 over epsilon iterations. And what's the total cost of those iterations? Ignoring the sampling probabilities, it's about order d squared log 1 over epsilon. Okay, because each step costs us order d. So what this is telling us is that we could drive the error in the actual solution down to a level epsilon with a number of iterations that doesn't even depend on the number of equations. Maybe it's not surprising, right? Like a lot of these equations are sort of beside the point. The system's consistent. But what it's telling us is that we only need to do this amount of work to get a reasonable solution. And that's pretty good because, nominally the cost of solving a linear system is if I missed something, no, I think this is right, is higher. So at least for these very nice systems, we actually get a pretty efficient algorithm for solving them. Okay, and it is the cost independent of the number of equations. Yeah, did I drop something somewhere?
We have the independence for the sampling here, right?
Yeah. Independence for the sampling?
So n dependence on n?
If you want to compute the sampling probabilities, yes, that's right. You need to pay dn here. So this is for the iteration without the cost of computing the probabilities. Absolutely. But that cost, yeah, right? So if you imagine that n is, if it's like a square system or n is closer to d, it's d squared. So this is kind of the same order as this. It's only when there are a ton of equations that that dominates this cost. Okay. Now there is a very strong hypothesis here that this is a very easy problem. Okay. Condition number constant is the easiest kind of linear system. And of course, as the condition number goes up, you pay very heavily. Okay. So there's no free lunch here. All right, any questions? Yeah.
What if B is not in the range of A? Because injectivity is, I think, a fair assumption, but
Yeah.
having B be exact.
Yeah, here's what happens. So the algorithm converges to a horizon around the optimal solution. So the solution is unique if the matrix is injective. So you converge to some radius around the solution, then you maybe stall out. If you don't want that to happen, there are other things you can do, like averaging iterates and things like this that will fix that problem, but then it screws up the convergence rate. So yeah, great question. All right, want to prove this theorem? Yeah, let's go. All right. Cool. So can erase all of our control rules, and I'm going to show you the proof, roughly the proof that Strummer and Verschinen proposed. So this has been a very popular algorithm because this proof is elegant and it inspired a lot of people. Again, I have some questions about the actual significance of this for practical computations, but don't need to. All right. We can write the update rule as ET equals XT minus X star. So instead of looking at the iterates themselves, we want to look at the distance from the iterate to the error, to the optimal point. So we're going to track ET. And using the update rule, we see that this is XT minus 1 minus X star minus this stuff here. So this is AJT, XT minus 1 minus X star. So here's the XT minus 1. The X star comes from the fact that the system is consistent. So AJX star is equal to BJ. So that follows from the assumption here. And so that's where we get the X star from. We've got the normalization. And we've got the a vector correction here. This is good news. So we've got 2 copies of XT of the new error, or the old error, ET minus 1, here and here. And then we've got to understand what this stuff looks like. So let's rewrite this using matrix notation. So we get ET minus 1 minus AJT transpose divided by norm AJT squared times the previous error. And this is a rank 1 matrix with trace 1. It's positive. So what is it? Yeah. A transpose divided by the squared norm of A is what kind of matrix? It's an orthogonal projector onto the range of, onto this vector. Okay, so we're going to write this to emphasize that point. So this is an ortho projector, which I've given a name. And so we see that the error is being projected at each step, which is good news because that means for sure the error is going down in Euclidean norm. And we'd like to understand how far it goes down. Okay, so using the Pythagorean theorem, we see that the new error is equal to the previous error. And I'm going to write this out as a quadratic form. And the reason that I only have one copy of this projector here is because it's a projector. So when I square it, I get the same thing back. Okay? Projectors are idempotent. Okay? So the great thing about this formula is that the projector appears linearly, which is going to make our lives easier. Okay? So great. Any questions on this part of the calculation or this expression? So this is our evolution equation for the error in terms of the projector onto the equation that we've chosen. All right. Now, at this point, the classical analysis sort of grinds to a halt because it's hard to understand what this projector is doing with any of these other control rules I described. Now, in this case, with the random control rule, we can actually compute the expectation of this projector. So the expectation over the randomness at step t of the projector is given by the law of total probability. So we've got the projector onto the ith equation times the probability of selecting the ith equation. So that's just the definition of expectation in terms of the values of the distribution, their probabilities. Now, the projectors are of the form AI transpose, divided by the squared norm of AI. The probabilities here are AI squared divided by the Frobenius norm of A squared, because we were clever. And what happens? We have this cancellation between these terms here. And so what happens is that the Frobenius norm pops out the front. We sum over the indices I of AI transpose, and this is the Gram matrix A transpose A. The stars switch places because of my weird convention for the transpose on the rows. Okay, so that was easy. And this important sampling distribution ensures that this happens. Now, why is this interesting? This is telling us that the projector, on average, gets its share of the Gram matrix. Okay? So this is the trace of this matrix. So this is somehow a normalization. And what we're seeing here is that with this random control rule, on average, the projector that appears in this formula gets its share of the matrix in the least squares problem. And because of that, the analysis of the algorithm depends only on the properties of the matrix A, which is kind of what you want. All right, so we can erase the iteration now and continue. So bilinearity the expectation over the randomness at step t of the squared error is equal to the formula that we presented before, where we now use linearity to pull the averaging in through the inner product and here onto the matrix. So just put an expectation here because the control, J, that we choose at this step is independent from everything else. All of these other things are constants. We have fresh randomness here. And so ET minus 1 has nothing to do with the row J that we pick. So we can pull the expectation through ET minus 1. It lands here. And then again, using linearity, we get to put the expectation onto the projector. OK. And this is because we are using fresh randomness in each step. Okay, so we're only averaging over the randomness in the current step and not any of the previous steps. We imagine that they're frozen in time. Okay, good. Now we know what this is. This is ET minus 1, I minus A star A divided by the Frobenius norm of A squared times ET minus 1. Now this is good. It's a quadratic form, so we know how to bound these things. We need the maximum eigenvalue of the matrix, and we need the squared norm of the thing on the outside. So we have lambda 1 of I minus A star A over norm A Frobenius norm squared times the norm of the previous guy. What's the maximum eigenvalue of this? Well, it's 1 minus the maximum eigenvalue of this, which is, sorry, it's 1 minus the minimum eigenvalue of this, which is sigma min squared, divided by Frobenius norm of A. So let's write that out. It's 1 minus sigma min squared of A, divided by A Frobenius norm squared, times ET minus 1. And of course, this is the demo condition number minus 2. So it just sort of pops out of this argument. OK. Any questions on this calculation? So what we've seen here is that by choosing this careful importance sampling distribution, that we can make sure that at each step, our update gets its share of the total matrix involved in the least squares problem. So we always make some progress. And that's what this equation tells us. On average, over the random row, the error is reduced by a constant factor from the previous error. So this is progress on average. That's what makes this work. At each step, no matter what happened before, we always do a little bit better. And the amount better, because of our careful importance sampling distribution, only depends on geometric properties of the matrix A. Okay? Now, in short, we have this statement here. Oops. So this is a conditional expectation. What do you call a sequence that satisfies this kind of property? Random sequence that satisfies this inequality? It's a super martingale. OK, so strangely, super martingales go downhill, not uphill, because they are connected to superharmonic functions. OK, but so super martingales go downhill, and so super martingales have a positive super martingale, like this error, has an incredible convergence property. It converges asymptotically almost surely at a rate that is essentially this. But we can do something a little bit simpler and just unroll this recursion by now taking the total expectation instead of the partial expectation. And so, in fact, we can even just cross out the conditioning now and get the expectation here on the right. So using the Tower rule for conditional expectation. And so now we see that the total expectation of the error is related to the previous expectation. And then we unroll this recursion to obtain this result. OK. Any questions on this? All right, so that is the proof that the randomized catch-harness method converges to a solution to a consistent least squares problem by making progress at each step. The proof is actually very closely related to the analysis of stochastic gradient descent, but it does take into account the special form of the step size here. And we obtain this really elegant statement in terms of the linear algebraic properties of the matrix A. Okay, progress on average. So now we will take a break. And afterward, we'll talk about an algorithm for low-rank matrix approximation that also makes random choices at each step to ensure progress on average toward a solution. All right, you have some coffee. Called randomly pivoted Cholesky. And I'll explain the context for this. It is a very, very natural algorithm that has a somewhat subtle history, but is more or less been unknown and untried. And yet, it's an excellent example of this progress on average paradigm, and it works extremely well in practice. So what is this algorithm? What are we trying to do? So we're going to move back to the case where we have a positive semi-definite real symmetric matrix. And in this case, our access model is entry evaluations. So you can ask for the JK entry of the matrix and compute it. But you pay every single time you look at an entry of the matrix. Right? So this is very different from the matrix vector multiply model we talked about before. Here, you could compute a matrix vector multiply if you want, but you have to evaluate all the entries to do that every single time. And that's going to make you sad. So what is an example of a problem where this access model arises? Okay. So these come up most commonly in kernel methods for machine learning. So in this case, A is some kernel function phi evaluated at two data points, xj and xk. So in this case, the jk entry of A is some kernel function phi evaluated at two data points, indexed by xj and xk. And to compute each entry of this kernel matrix, you have to evaluate this function for this pair of data points. So you pay every single time. All right? So any kind of kernel method confronts this challenge. So kernel matrices are really an excellent example of a setting where you pay to look at each entry, and you really need to design algorithms that avoid that if possible. Okay, I'm not going to talk about kernel methods here. I just want to emphasize that this is motivated by a real challenge in scientific machine learning. Okay, so what is our goal here? Our goal is to compute a low-rank approximation of the matrix A that competes with the best possible low-rank approximation and requires a minimal number of entry evaluations. Okay. So we're going to try and approximate the matrix without looking at very much of it. Okay. Now, you can't do this in general because for a rectangular matrix, there could be stuff hiding in the parts that you don't look at. So if you only look at this part of the matrix, there could be a huge entry over here that you never see. And so if you don't have some evidence about where the important stuff is, you can't do this for rectangular matrices. For positive semi-definite matrices, though, there is a prospect of accomplishing this goal because of the Hadamard inequality, which tells us that the magnitude of the JK entry of the matrix is dominated by the product of the corresponding diagonal entries. Okay, so an entry of this matrix can only be large if the corresponding diagonal entries are large. Conversely, if the corresponding diagonal entries are small, you're guaranteed that that entry is small. Okay? There's a bit of an asymmetry here where big diagonal entries do not guarantee large off-diagonal entries, but they do forbid large diagonal entries. And so it's not a very perfect guide, but it does tell you that just knowing the diagonal tells you where you might need to look. And this is a huge difference between the positive semi-definite case and the general case. So that's one reason that we're in this context. And it also fits pretty neatly with kernel methods, right? Because a lot of kernel matrices are indeed positive semi-definite. Now, the reason we might be interested in computing a low-rank approximation of a kernel matrix is to accelerate downstream kernel computations. So if you want to do kernel spectral clustering or kernel ridge regression or any of these other kinds of algorithms, it might be a lot faster to replace the full matrix by a low-rank proxy because they're more efficient to represent and to perform linear algebra on. Okay, so that's the high-level picture here. But as I said, we're not really going to talk much about the application. And we're going to measure error here using the trace norm. So we're going to be looking for an approximation A hat, which satisfies the property that it is comparable with the best low-rank approximation. And we're also going to insist that the approximation is positive semi-definite and it is smaller than the matrix A in the positive semi-definite order. So I don't really want to stress these points. The main consequence is that this is a positive matrix, so its trace is indeed a norm. It tells us how much total eigenvalue we missed. And we're going to compare with the best approximation of A by a rank R matrix, how much total eigenvalue we miss in that approximation. So this is the error guarantee that we're going to try and achieve. We're going to allow the rank of our approximation, A hat, to be a bit bigger than the rank of R of the approximation we're comparing with, and this flexibility allows us to design efficient algorithms. So I'll connect these things later so you can understand the exact relationship between the rank of this and the target rank. Okay, so this is the way we're going to measure error in this setting. It's very natural for kernel methods to do this. Okay, any questions on this preamble? All right, good. So there's a very beautiful classic algorithm for low-rank approximation, which is called pivoted partial Cholesky. So this is related to Cholesky's method for factorizing a positive semi-definite matrix into lower triangular factors. So you know this algorithm, I hope? You know Cholesky's method? Okay. So here's a reminder about what this algorithm is doing. So imagine that you start out with a matrix A naught, which we're going to write in partition form. So the idea behind Cholesky's algorithm is that we're going to reduce it by eliminating a column. Okay? So we're going to try and build an approximation out of columns of this matrix by picking a column, removing its influence, and then taking the column we extracted and putting it into our approximation. So the way this works is that imagine we want to build an approximation using the first column. In this case, we take this column out and we build a matrix approximation of the form A21, A21 transpose divided by A11. So this is our initial approximation using just this first column. Okay? Why this form? Well, it's a positive semi-definite approximation, and it has some optimality properties that I'm not going to talk about in detail. But the idea is that if we wanted to eliminate this column, we wanted to use it to build an approximation, somehow this is a natural way to do that. So this is an approximation using just the, sorry, some typo. It should be 1 over A11, A11, A21, A11, A21 transpose. Sorry, here's the approximation. Okay, so it's rank 1, has this form. You can see also by dividing out the A11, we get a copy of A11 in the first position. And so how much of the matrix is left after we do this? Well, this approximation also has the beautiful property that it really does eliminate the first row and column. Okay, so that's one reason you might choose this, is that it's low rank and it kills off everything in the column that we have chosen to eliminate. What is left? Well, it's A22 minus A1 hat. So, no, I should not write it this way. Sorry, my notes are a little bit sloppy. I apologize. So we have got zeros here, and then the part that's left is A22 minus A21, A21 transpose divided by A11. Okay, good. So in short, the Cholesky method builds an approximation by picking a column, sticking that column into the approximation, and then removing its influence from the matrix. A very important feature of this algorithm is that when we start with a positive semi-definite matrix, this elimination step leaves us with a positive semi-definite matrix, and in fact this has some optimality properties, as I mentioned. What do you call this thing here? It's called the Schur complement of A11 in this matrix. Okay, so as another aside, this approximation that we build here is also a very special thing. It's called a Nystrom approximation. I'm not going to go into any detail about Nystrom approximations here, but they are a very natural way to produce approximations of positive semi-definite matrices using columns. So here's the one step of the Cholesky algorithm. We could just repeat this process. So now we come to this. Oh, I guess one other thing I should say. To perform this elimination step, all we need to do is evaluate the entries in this first column. Okay? So there are not a lot of entries required to perform this reduction. We only look at the first column and then we're done. Okay? We don't need to look at anything else. Okay? Now, once we've removed the first column, we can look at the residual matrix here, A1, no hat, and we can perform the same step. We can pick a column to eliminate, we can extract that column, we can add it to the approximation, we can remove its influence, and repeat. I'm going to write down pseudocode for this in just a second so it's a little clearer what's going on. I just wanted to illustrate in this specific case. Is it clear what we're doing here? All right. So let's write down the procedure in conceptual form. This is not actually how you implement it, but it's a lot easier to understand what's going on. So the procedure is that in the initial step, we set our first approximation A hat to be 0, and we set our initial matrix to be the input matrix that we're trying to approximate. So the residuals are going to go down as we eliminate columns from the matrix. The approximation is going to get bigger as we add rank 1 corrections. So how does this work? We select a pivot column to eliminate. So ST is the index of the column. So in this case, S1 is equal to 1. We're eliminating the first column. And we update the approximation by taking the previous approximation and adding the rank 1 matrix, AT minus 1, column ST, AT minus 1, row ST, because these matrices are symmetric. This is the transpose of this. And we need to normalize by the diagonal entry of the current approximation in this position. So A11 here is here in the denominator, and this column vector and row vector in this case are here and here. Okay? This is just a more general formula that describes the procedure we already illustrated. Okay, so this is the correction to the approximation. At each step we add a rank 1 update. And how do we update the residual? We take the previous residual and we subtract to the same update. All right, good. So we add the update, we remove the update. This has the effect of maintaining the positive semi-definite property of the matrix. And it actually zeroes out the ST column, just like over here. All right. Now, in the ordinary Cholesky procedure, you just cycle through the columns one after the next. And as you zero things out, the columns get shorter and shorter and shorter. And so you get a lower triangular approximation. OK, so that's how Cholesky works. You learned about this in numerical linear algebra. The difference between the pivoted version and the simple version is that you don't necessarily pick the columns here in the given order. You decide which column to pick. We'll talk about that in just a second. The other difference is that we stop after case steps. Okay, so now these approximations, we hope, are doing a good job in representing the matrix A, and we would like to choose the pivots to ensure that we produce a good approximation. That's our job. So we want to pick columns so that a small number of columns do a good job approximating the whole matrix. Got it? Awesome. Okay. Now, something that's not obvious in my account here is that to implement this procedure, you only need to evaluate one column of the input matrix. That's not what I've written here. Here I've written this in terms of the residuals. That's not how you implement this procedure. So this requires one column evaluation at each step, plus some extra arithmetic. So you're implicitly computing the column of the residual by taking the column out of the initial matrix. Okay? So this takes some thought. It's not obvious, but the point is that this is an algorithm that you can implement with very few entry evaluations, even though that's not what's written here. Okay? So each step, we evaluate one column. And the hope is by only evaluating k columns, we have produced a good approximation without ever looking at most of the matrix. Okay. You willing to believe that? Maybe. Okay. Good. So, all right. What's missing from this account of the algorithm? Which columns? What's the pivot rule? So to specify this algorithm, we need a pivoting rule. Proposals?
Sample the diagonal at the beginning.
So you already know the answer. Let's dial back to, I don't know, say 1990 or something. Or I actually don't know when people started using the partial Cholesky procedure to produce approximations. Cholesky was actually interested in solving least squares problems that arose from surveying. He was a surveyor with the French army. But I know that the classic pivot rules date back at least 35 years. So any thoughts what someone might have done beforehand? Largest diagonal entry. Great. So greedy pivoting. So ST is in the arg max of the diagonal entries of the current residual. So it's very important to note this is an adaptive pivoting rule. At every step, we look at the residual, we look at its diagonal entries, and we pick the position of the biggest diagonal entry, and we eliminate it. Why does this make sense conceptually? Yeah, Kobe.
Because of that inequality.
Yeah. Hadamard justifies this. The big diagonal entries signal the columns that could have big entries. The small diagonal entries tell us that those columns cannot have large entries. Sorry, did I just say that backward? The large diagonal entries signal columns that could have large off-diagonal entries. The small diagonal entries guarantee that the column has no large entry. All the entries are small. Okay, so that's why this is a sensible thing to do. I've seen this in the literature dating back at least as far as 1990. Chaim has a survey on Cholesky methods where this is quite explicit. Okay, great. So this is what you would call an exploitative method in the machine learning parlance. You believe that the diagonal entries are significant and you're going to exploit them hard. You're always going to pick the biggest one. Okay, more thoughts. Okay, let's fast forward to 2000. You are a machine learner and you're trying to build kernel methods. What's the first thing you think to do? Well, in machine learning, statistical learning, all data points are the same, right? They're all IID from some distribution, obviously. So they're all kind of the same as each other. So what does that suggest that you might do?
Uniformly random.
We're going to pick them uniformly at random. Okay, uniform pivoting. So in this case, ST is chosen uniformly from 1 up to n. This certainly appeared as early as, say, 2001 in a paper Williams and Seeger. And this is a pure explore proposal, right? You're not using any information you've acquired. You're just like, that's nice. That's nice. All right. Good. Now, I think Alex has already answered our question. So what's a more thoughtful thing to do?
You sample it according to the data.
Yeah, we're going to do important sampling based on the current diagonal. All right. RPC is the rule that ST is chosen to be the nth column with probability proportional to the diagonal of the current residual. Okay, so remember, PSD matrices have non-negative diagonal entries, so this really does define a pre-probability distribution. Normalizing by the sum of the diagonals gives us an honest-to-God probability distribution on the diagonal. And we're just going to sample ST at random from that distribution. Okay? So this is a mixture of exploit and explore. So it's based on the intuition that the diagonal entries provide information about which columns might be important, but it's not a perfect signal. And by exploring some of the smaller entries, we might actually be able to find more of the energy in the matrix than if we just always brutally pick the biggest one. Okay. The history of this proposal is a subject of some contention. So I will say that algorithms like this appeared in a paper of Deshpande and Vempala around 2006. The algorithm they described is really more along the lines of what you would call randomly pivoted QR factorization. It has a different construction and a different computational profile from this algorithm. This particular procedure was mentioned offhand by Musco and Woodruff in 2017, where it was set up as a straw man that they are going to complain about. They did not analyze or implement it. It appeared in a different context in a paper of Poulsen from around 2020 on sampling from determinantal point processes. And so far as I can tell, the first time anyone actually took this seriously as a possible computational method was when I told my group to look at this as a straw man, and they're like, we shouldn't do anything else, this works great. So we did some numerical work and discovered that this is actually a very effective method for low-rank matrix approximation. So we set out to understand why that is. Surprisingly, even though this seems like a very natural procedure, it really has never been studied. So that's what I want to communicate here. But I want to try and give appropriate credit to the forebears. All right, good. Any question about what this algorithm is doing? Sorry, one more time?
How important is the adaptation?
Very important, yeah. So what happens is that as you remove columns, you are revealing structure that you couldn't see before. Okay, so if you think about a kernel matrix associated to clustered data points, so the kernel is big on diagonal blocks associated with these data points, and it's big on the diagonal block associated with these data points. After you pick one of these data points and you remove it from the kernel matrix, you've already explained these data points, but you couldn't see that at first. Okay? So you pick this guy, it explains the other two, and then these guys are sticking out on the diagonal. And so it's obvious that you need to pick one of these guys. Okay? And they're all kind of the same, it doesn't really matter which one you pick. But this would not be visible to you that these are different until you actually look. Just one other quick comment. You can do this with one evaluation of the diagonal at the beginning, and then you can maintain the diagonal for free. So there's no extra cost associated with this. Yeah?
This is equivalent after you pick your however many
Yeah.
pivots. You sampling your pivots, like this collection of pivots, is usually from a determinable point process.
No, it is not sampled from a DPP. It's a different distribution. It's marginally a 1 DPP, but it's not the same distribution. It's some other point process. Yeah. It's not a DPP. It's a DPP if the matrix A is an orthogonal projector. That's what Poulsen understood. But only if A is an orthogonal projector does this correspond with a KDPP. So this is getting a little into the weeds, so I would propose that we talk about why this works. I'm not going to give a full proof, but I want you to understand why this is a progress on average strategy. Okay, shall we do that? Okay, great. So writing too big. Okay, so why does this work? So this is, again, a progress on average strategy. And the way we're going to measure progress is by defining the expected residual map. Which is phi of A, which reports the expectation of the residual after one step, given that we start at a matrix A. So what does this mean? I initialize this RPC algorithm with a matrix A. I take one step, and I average over the choice of columns. And the observation is that phi of A is equal to the expectation. So what do we need to do? We need to sum over the columns as from 1 to n. At each step, the residual is the previous guy, A, minus the correction. So A, if we pick the S column, here's the correction. What's the probability that we have picked the S column? That's the thing I just erased. It is the previous matrix, the residual, the S diagonal entry, divided by the trace of the previous matrix. Okay? So here are the sampling probabilities. We sample the S column in proportion to its diagonal entry. And this is the correction we make if we have sampled the S column. Now, we can simplify this. We obtain A minus, well, these guys cancel. So you can see why this is a natural choice of sampling probabilities for this algorithm. And we obtain 1 over trace A, sum from S equals 1 to n, outer product of this column and this row. And what is this? This is the square of the matrix A, because we're summing through the inner columns. Okay? So the expected residual map has the form A minus 1 over trace A times A squared. So what you see as the expected residual is a matrix that is smaller than the matrix we started out with, because we're subtracting something positive from it. Make sense? At each step, we subtract something that gets its share of the total matrix. And if we compute the trace, so the expected trace of the residual after one step is equal to the trace at the initial point, so the trace here, minus the trace of A squared divided by the trace of A. One copy here, one copy here, so we got the trace of A squared. So on average, the trace of the residual, the error after one step of this procedure, is related to the error after 0 steps. Error after 0 steps, error after 1 step. Okay? And you can see that we've reduced the error. Now, in the worst case, this is always smaller than 1 minus 1 over n times the trace of A. Okay? So for sure, we're always making progress. And this is an extremal problem involving the eigenvalues of the matrix. You can check this. But this isn't informative, because this would suggest you need n steps of this algorithm. You have to eliminate n columns before you make any progress. So this doesn't help. But this formula tells you something. You make progress when the current residual has spiky eigenvalues. So the situation where the trace of the square is a lot bigger than the square of the trace is when some of the eigenvalues are pretty big and the other ones are maybe smaller. So that means there's low rank stuff you can find here. This bound occurs when the eigenvalues are all the same. That's when you're sad. Okay? But when the matrix A has big eigenvalues, there's stuff to find and you make a lot of progress as encapsulated by this ratio. Okay? So this is just an intuition, but it's very clear that from this analysis, the algorithm, on average, improves your situation by reducing the trace error, which is your goal. Remember, the trace is the measure of error that we're using here. Okay. And so long as there's still low-rank stuff to find, the algorithms are going to keep chewing away at the matrix. Okay. Using this to prove a theorem is actually quite difficult, so I'm not going to show you more of the details, but I wanted to communicate the idea. Any questions on what's happening here in this algorithm? Okay, let me write down a theorem that describes what this algorithm does. And then we'll wrap up for the day. Theorem. So for a PSD matrix A, for a target rank R, and for a suboptimality parameter epsilon, the expected trace of the error in approximating A with a rank K matrix obtained from this randomly pivoted Cholesky algorithm. So there's the expected error after K steps of RPC is bounded by 1 plus epsilon times the error in the best rank R approximation of A. Okay. So this is what you're comparing with. You are suboptimal by a factor of epsilon. Now what's the relationship between K and R? How many columns do you need to eliminate to get to the best rank R approximation error? The answer is that the number of columns you need is the target rank divided by epsilon. So a little bit more than the target rank. Think about epsilon as like 1. Plus the target rank times something that depends on the log of the suboptimality times some measure eta of the dynamic range of the matrix. So eta is the trace of the initial matrix divided by the trace of its best low rank approximation. And so you should think about this as a measure of dynamic range. So how far do you have to drive the trace down to get from the initial matrix to the best rank R approximation? And so what you see is that the number of columns you need, K, is roughly proportional to the rank of the approximation you're competing with. And you should think about this logarithm as a constant. Okay, so for example, if this is 10 to the minus 16th, the logarithm is like 37 or something. Okay, so it's not a big number. And so the interesting thing about this is that you only need to reveal K columns. So you only need order Kn entry evaluations to produce this approximation. Okay, you only look at K columns of the matrix and that's it. You never need to look at anything else. And yet you can still produce a near optimal approximation using this procedure. And so what you see is happening here is that at each step, so long as there's still something in the matrix to find, on average, you find some of it, and you drive down the residual. Progress on average. And while there's still more to find, you keep making progress typically. Maybe you screw up at one step. Doesn't matter. You'll find it next time. And this algorithm is, like I said, it's been overlooked, and it's surprisingly effective for producing low-rank approximations of kernel matrices. And in comparison with these other kinds of pivoting strategies, greedy and uniform, it works in situations where they fail. So this algorithm always has a guarantee where the other ones have failure modes that come from either over-exploiting or over-exploring. Okay, you may.
Does it help to make Monte Carlo, to do Monte Carlo together with this algorithm?
Monte Carlo for what?
I mean, repeating this computation a number of times.
Oh, that's a good question. I think that actually it is typically going to be better just to put your energy into making a higher rank approximation rather than repeating the algorithm and hoping that one of them is good. The reason is that you can take the approximation you have, if it's higher rank, and then truncate the rank by using an eigenvalue decomposition or something like this. Okay, so I've talked long enough. That's it for progress on average. Next time, we're going to talk about random dimension reduction, which is perhaps the most well-known example of how you use randomness for linear algebra computations, and that's why I saved it for last. I wanted to tell you about some things that maybe are less familiar. Thank you so much for your attention. I will see you tomorrow.